We are going to tackle some information from 1.4. The book calls it writing functions from functions. I'm going to call it operations with functions. As we're going through this, here's what I want you to think about. Given any two functions, can you perform every operation on them? In other words, can you add them? Can you subtract them? Can you multiply them? Can you divide them? Can you compose them? So in the first Delta Math, you were given three functions, you were given the opportunity to practice some stuff with functions. So the first function I'm going to give you is x squared minus 9. I'm going to give you a function g of x. Remember, those letters are just the names of the functions, right? When we use y and every function is called y, it's hard to distinguish them. So instead we use g of x and f of x and things like that. H of x, for example, to name the functions. And those names then allow us to use the notation a little differently. So for example, this notation, f plus g of x, means that I add f of x to g of x ta-da, right? And just adding them. Same thing with subtracting, although I might get a little bit more organized with my parentheses to make sure I don't lose any negatives along the way. If I am working with, so in both of those cases, there were like terms we could collect. But if I'm doing something like this, then that's about as far as I'm going to get with that. I can't do too much more because there's no like terms to collect. It's hard to do anything with the square root, really. Then you practice some stuff with multiplying, right? Fg of x squared minus 9 times x plus 3. A lot of different ways to attack that with the result of x squared plus 3x squared, x to the third plus 3x squared minus 9x minus 27. Right? We just multiply them. If you like something called the box method, I'm going to set up a 2x2 box because each of those functions has two terms. Feels a lot like lattice from when you were a smaller mathematician. And then you can look for like terms in here. We didn't have any, but if we would have, that's where we would have spotted them. So that's multiplying. And in all of those cases, we pretty much just kind of have that. We can also divide them. F divided by g of x. And f divided by g is going to end up as x squared minus 9 over x plus 3. And x squared minus 9, I can think about as x minus 3, x plus 3. And so when things cancel, I just get x minus 3. Tricky thing here is that we have to consider the fact that this original function had something in the denominator. And the denominator in a fraction can never equal 0. It's a rule. Can't divide by 0. It's a rule on the domain. So in this case, because the denominator cannot equal 0, x plus 3 cannot equal 0, which means x can never equal negative 3. Even though it cancels out just fine, it can never equal -3 because of how the original function was set up. Now, hopefully most of that felt pretty familiar from things you did in Delta Math and whatnot. But we're going to take a deeper dive in some other types of function operations that are a little less familiar. So the first is composition. So composition is kind of function substitution on steroids. And it relies a lot on your ability to navigate function notation. So specifically, composition is the process of inputting one function into another. And by inputting, I mean substituting. Okay, so I'm going to talk through two functions. F of x is going to be 6x plus 5, and g of x is going to be x squared minus x. So we've got f of x equals 6x plus 5, and g of x equals x squared minus x. And the first thing we're going to do here is we are going to do f of g of x. So right there, it looks like fog. It is pronounced f of g. That's how we read it, right? We want to be able to read it. So then what it means is this. It means f of g of x. And it means that g of x is going to get plugged into f. So g of x here, x squared minus x, is going to get plugged into f. So here's f of x. Oops. There we go. And in that f of x, there's one spot where I can put an x. Or let me try that again. There's one place to substitute into. It's right there. So I'm going to use that function f, and wherever x was, I'm going to put parentheses. And inside those parentheses is going to live g. I'm doing substitution on steroids, right? Instead of just substituting a number, I'm substituting a lot of stuff, an entire function. Then the fabulous distributive property that we all know and love will bring that 6 to both parts, and there's our final answer. Okay. We can also go the other way. We can say g of f of x. And when we say that, that means that g of f is now the inside function. So f is going to be put into g. Now there are two places in g that have an x on them, which means I'm going to need two sets of parentheses for my substitution. Six x plus 5 is going to go everywhere there was an x. Okay. And then we can clean this up a little bit. Thanks to some FOIL and some distributive property. If that doesn't feel totally comfortable to you, you will get better at it, I promise. And then we'll just collect our like terms and kind of finish it off. The only other one I was going to show you and look at real quick, it's kind of a weird one, but it's kind of cool too. So here's what we're going to do. We're going to do f of x. Okay? And so that means that I'm going to take f, I'm going to take f and plug it into itself. So this f right there is going to live inside that f. So I have 6x plus 5, and I'm going to put a 6x plus 5 inside there. And then again, use the distributive property. And I'm going to collect some like terms. But composition is about substituting information, one piece of information into another piece of information, or one function into another, and then simplifying it to the best of our ability. Okay? Composition has a partner in crime, or maybe it's an evil twin, I don't know what you want to say, called decomposition. Composition puts two functions together. The evil twin decomposition is the process of splitting a function, a fairly complex function, into two smaller functions. So we are going to, basically, we're going to be given f of g of x, and we need to find f of x and g of x. Because of how composition works, g of x is essentially the inside function living inside f. And when we say inside, we can say it lives inside parentheses in f, or it lives inside a square root, or it lives inside absolute value, or something like that. So g of f is going to serve to be our inside function. F of x will be our outside function. And here is what I mean. The first example we're going to look at looks like this. F of g of x is what we're given. Whoops, there we go. And it looks like this. X squared plus 1 minus 3. So we need to determine which function, g of x, is living inside another function. And so when I read the square root of, and then x squared plus 1 minus 3, x squared plus 1 is underneath the square root. And so I'm going to think of that as my g of x equals x squared plus 1. That's the inside function. Here's what that leaves me with. Essentially, the framework around that green, everything else that isn't green. There was a square root and a minus 3 in the back. And in order to finish this off, I need to put an x under the square root. And so if I think about composition and plugging in g of x into f of x, I want to make sure I have a spot to put it, and that's why I need something under the square root. Okay. Here's a second example. F of g of x equals x plus 5. Now immediately when I notice that something is inside parentheses, that should be a pretty good clue that I can see my inside function, because whatever is inside those parentheses is going to be what we want. Okay, so I've got something like this. I've got x plus 5 squared minus 5 times x plus 5. So think about living inside. I'm living inside these parentheses, like as if I've been substituted. So our g of x here is x plus 5. Well, now I need to look at what's left. So my f of x, here's what I see. I see that I had a parentheses, that the x plus 5 went into 11, and then I see a 5 with another set of parentheses, right? And those parentheses used to hold my green functions. But now I'm breaking it apart. So I've pulled those out as their own. Okay. Those parentheses weren't like that in the original f of x, but everywhere a parentheses was or everywhere a green box went, I need to use an x. Okay.